this up. All of a sudden it's March. Crazy. Although in my mind it was already March after reading break. It's like, oh, that little blip of February doesn't count. April doesn't count. Just need to focus on March. Okay, so we are in a little bit of a pickle for a nickel, because we're quite a bit behind. I want to spend time talking about the rest of those exercises that I gave you, the chapter 6 examples. I still have a few handouts here, just a couple. 1, 2, 3, 4, in case you don't have one of the chapter 6 examples. But we really need to start talking about the binomial and the Poisson distribution. So what I kind of decided this morning, so yesterday I was like, no, I'm going to stick to my guns. I'm going to do these examples, and it's going to take the time it takes. And then this morning I was like, you know what? I think I should just post a video going through those exercises, question 2 and 3. So then you can review them on your own, and then we can move on and talk about some new stuff, right? Because we did spend all of last week talking about Z scores, the Z distribution, using the Z table, Z, so much Z, right? And so what I want to do is I will post a video with the solutions, and then of course I'll post just the PDF of the solutions as well for questions 2 and 3. But just because I want to talk you through it, right, in case it's not clear, hey, where did you pull all this stuff from? That's why I'll post this video with the solutions to questions number 2 and 3. On the chapter 6 examples handout. Just as a side note, assignment number 6, bless you, is due on Friday. Okay. So far you can do up to question 8, and depending on how far we get today or maybe Wednesday, by the end of this week for sure you'll be able to do the rest of it. Okay. So you can do up to question number 8. And by the end of the week, yes? Is that lab table on Friday, or is it assignment? That might be. Like, is it due on the Sunday instead? But I bumped it. Okay. Yeah, I bumped it, but I can't remember. I thought I bumped it to Friday, but now that I think about it, maybe I bumped it to Sunday, Monday. Sold. Monday, exclamation mark. Okay. March 9th. Aha. I'll finish this sentence and then I'll put a note about that as well. Thank you. By the end of the week, you will be able to do all of it. And then lab number 5. is the one that's due on Friday. For real this time. Lab number 5 is due on Friday. Good. Okay. So, like I said, we won't really review, but I'll post that video and you can review it on your own. So what I want to do is I want to get into kind of the rest of chapter 6. So section 6.2 is really just a brief little method of checking if we have a normal distribution, right? And so a lot of our assumptions are going to be hinging on, do we have a normal distribution or not? Or a lot of the things that we do will assume that we have a normal distribution. So what's section 6.2 called? Probably checking normality or something like that. So many of the methods, or many of the, methods we will use in this course assume that our data follows a normal distribution. Assume that our data follows a normal distribution. Often it'll just say in the question, right? So far, the questions that we've looked at, if you have a read through the chapter 6 examples that I've given you, right? It says, hey, this follows a normal distribution, don't worry about it, right? But there's going to be times where we have to check that it follows a normal distribution, right? Probably more in the real world than the problems that we have here, right? And so the first way, we have 2 common ways to check normality. First one being you make a histogram and you visually assess it, right? And so make a histogram. And then just make sure it looks approximately normal. Make a histogram to see the distribution. If you've done that and you're not quite sure, or you want to confirm that it follows a normal distribution, there are a lot of other tests that we could do, but one kind of mini one, because we haven't talked about hypothesis testing yet, so there's a lot of hypothesis testing ways that we could do it, but we haven't talked about that yet. So the other main one that we have is using a quantile plot. So a quantile plot is also called a QQ plot. QQ. Oh. What the QQ plot does is it makes a scatter plot of your actual, if you think about the histogram, right? So here, let's talk about the QQ plot. It's going to be a scatter plot of the actual values, right? Or you can call them observed if you want, versus the theoretical values. what that means is if we think about a histogram, right? Let's do little. Let's have a histogram like this. Right. So here's our histogram. These values here, let's think of those as our actual values. Now it takes each of the observed values, but this is just to get an idea of what's going on, right? And so these light blue dots are the actual values. Then, and now I'm going to draw this perfect normal distribution because it calculates the mean and the standard deviation of your data and then just draws the normal distribution that would follow that mean and standard deviation. So here might look something like this. So here, this is the theoretical which is a normal distribution, normal with the same mean, mean and standard deviation as your data. So what it does is it looks at the difference between these, right? So here, for a lot of these points, right, these points are kind of bang on where we would expect them to be. Of course, I just made this up, so, oh, surprise. Here, the actual was a little bit higher than the theoretical, right? And so, but in general, we're hoping to see that these actual values, if it follows a normal distribution, would be roughly the same as the theoretical values, right? And so at this point, it was a little bit higher than here, right? Or sorry, lower than here. But in general, right, if we plot these, what are we expecting to see? We would expect them to follow just this diagonal line, right? Where x equals y. So then you've just got this diagonal line. And so it gets confusing because I had to do that, and then now I can do the QQ plot, right? And so what we do is we can draw just a diagonal line. So if the data follows a normal distribution the points will fall on the diagonal line. Will fall on the diagonal line. Oops. I'm gonna squeeze it in here. You could have, so ideally, you know, we've got points kind of like that, right? There could be situations where you get some sort of skew around. And so here, if we have skewed data, right, meaning it's not normal, then our QQ plot might look something like this, where we've got our diagonal line, that's our ideal. Right? Doesn't help that I didn't draw a straight line. There. Ish. If you've got things that look like this, right? Kind of normal for a little bit, right, where it kind of gets close to that line, but there's obviously something else going on here, right? And I'm very sure, although I can't remember exactly, that the textbook goes through and shows you some examples of skewed distributions, okay? Here, there's no way that we can argue that this would be a normal distribution. There's only a little section where the lines are, or the points are on the line, right? And here it's above, here it's below, here it's above again. So we clearly don't have a normal distribution, and we would need to deal with that. But in general, a little bit of lift off in the tails is fine, okay? Because the tails are unpredictable, right? And so if we have something like this, right, where we would say it's approximately normal, if we add something like, and of course I'm talking about a QQ plot again, here's our diagonal line. Even if we had something kind of like this, right. We tolerate, tolerate. Oy, I'll rewrite it. We tolerate some slight deviation in the tails. Right. So we tolerate slight deviations in the tails. So here I would say this is approximately normal because it follows that line for a good chunk of the way. So you can use QQ plots as well as histograms, right? First thing you would do is just make a histogram of your data, make sure it looks normal. If it looks normal, then you can back it up and say, hey, I looked at my QQ plot, looks pretty good, right? And then keep going. But as far as other tools, and there are other tools that we could use, but that's for a later course. How about you? Any questions about the QQ plot? Checking normality. All right. So what I want to do then is talk about the binomial distribution. And you guys didn't know this, but you've been waiting a long time for this. You'll see in a little bit. So section 6.3 is on the binomial distribution. And just as a heads up, there will be a binomial distribution question on the final. So there will be one on test 2, right? And so the binomial distribution is going to be a kind of a big deal. And then the Poisson doesn't come up on the final. It comes up in the lab briefly this week. But we'll just kind of do what we have to with the Poisson and then get out. Spend our time on the binomial. So the binomial distribution, we've seen it before. So a binomial distribution is whenever we have just two possible outcomes, right? So you flip a coin, it's either heads or tails. Whenever you can classify something as a success or a failure, right? And those are your only two outcomes. So someone gets a disease or they don't, right? Someone wins the lottery or they don't. Someone gets an A on the test or they don't, right? Whenever we can boil it down to a success-failure situation, we can model it with a binomial distribution. Okay? So, whenever we can boil down the possible outcomes to success failure. Right. So for example, heads or tails. What did we say? A in the class, not an A in the class. Right? We did that where we used that trick where, okay, you get an A or you just didn't get an A, right? Even though there's other grades that you could get, right? We could boil it down to a success failure situation. You get a disease or you don't get a disease, obviously. You die or you don't, right? And so usually it's kind of morbid stuff that we're trying to model, right? But in general, right, as soon as you can boil it down to just two possible outcomes. So here we have two possible outcomes. So if we can boil it down to just the success failure situation, but also we have to assume that all these outcomes are independent of each other, right? And so we can't have those conditional probabilities that we dealt with before in probability, right? In the probability section, right? Now we're kind of back into it, but only briefly, promise. So whenever we can boil down the possible outcomes to success failure, and each of the trials are independent, I'll just say that a trial here would be each flip of a coin, for example. Each flip of a coin, right? So it's getting this very bulbous sentence that I'm getting at with examples thrown in. So we've got success failure, right? So two possible outcomes, and also each of the trials are independent, right? So every time that I flip a coin, that's independent of the next time that I flip a coin, right? And so what we're assuming is that you getting an A in this class is independent of the person next to you getting an A in the class, right? And so on and so forth. And so sometimes we just have to assume these things so that we can use a binomial distribution. And then sometimes it just won't be possible, right? Getting a disease, borderline, right? More likely to get a disease if, you know, your neighbor has a disease or whatever, right? So, but it's just one of the assumptions. So we can find probabilities. There it is, that word. We can find probabilities using the binomial distribution. Using the methods that we already had, what we could do is, let's say I flip a coin 3 times, right? And I want to know what's the probability of getting at least one tail, right? We know how to tackle that, right? You'd start with a tree diagram and you would have a tree diagram of your 3 flips. So for example, I flip a coin 3 times, what is the probability of, actually, I'll just say of one tail, just to start slow. We can use the methods that we already have. We already know. Such as a tree diagram. So I flip a coin 3 times. And so here at the top, I've got my first flip, flip number 1, which is, now we're going to start thinking of these as trials, just to use the same terminology. Oops, can't write it all today. Trial number 1. So I either get heads or I get tails. Okay. Then I flip again. Flip number 2 is trial number 2. Heads, tails, heads, tails. And then I flip again. 1, 2, 3, 1, 2, 3, 1, 2. Counting to 3, but only doing 2. Psych. Heads, tails, heads, tails, heads, tails, heads, tails. And so this, of course, is trial number 3. To answer this question, and we're not going to do it because we've already worked on these, right? And this is just to develop kind of an appreciation for the binomial distribution. Right? Because what do we have to do? Well, the probability of heads and the probability of tails, right? We assume that they're 50-50. So no matter which of these branches I head down, if I trickle down this way, right, heads and tails have the same probability. So at the end of each of these branches, what's nice is I'm going to have the same probability, right? And so we just need to figure out how many different combinations of these things have one tail, right? And so the first option would be here, yeah, I've got a heads, and then I need one tail, so here, that's one of the options. Heads, tails, well, I've got one tail, so now the next one I have to get is a head, right? Because I'm only allowed one tail, right? So far we've got 2 options that satisfy the criteria. And then if I start with a tail, then I have to get a head and a head because I'm only allowed one tail. And so I'm counting 3 different options that satisfy that criteria. So what we would do, right, is, well, here and here and here. Those would satisfy the criteria of one tail. Problem is, this gets out of hand, right? Because what if I say, okay, fine, you can do that, you can handle that, you can calculate it by hand, great. What if you flip it 10 times? Your tree diagram would be huge, right? It'd be massive. 10 flips, right? We're only at 3 flips, right? Imagine, I'll even write it down. Imagine the tree diagram for 10 flips. So here, the idea is going to stay the same, right? The probability of one tail and two heads, or just one tail and however many heads we need, right? That probability is going to stay the same, but we also have to take into account that I've got 3 different possible outcomes that satisfy the criteria, right? And so now I've got 3 combinations, right? So if we just outline, going back to, so in 3 trials, how many ways can we have 0 tails, oops, 1 tail, 2 tails, and 3 tails? Let's say a tail, let's call that a success. Sometimes it doesn't matter what you call a success, but whatever you're interested in will be a success, right? And so if we look, there's only one way to have no tails, right? That would be head, head, head. So 0 ways. Oh, sorry. I said 1, but I wrote 0. Thanks. 1 way. Singular. 1 tail, we just found that there's 3 ways to have 1 tail. And if we did it, right, 1 tail is the same as 2 heads. And if we just kind of argue it in our minds, or even just look at our tree diagram that we made, we would find that there's 3 ways to get 2 tails as well. And then for 3 tails, there's only 1 way, because we only have 3 trials. So these, what we've found here, are the number of possible combinations. So what I want to do now is I want to spring the formula on you guys, and then we'll dissect it, and we'll bring it back to this. Okay? And so to calculate the probability, of K, so I use a script K, of K successes in N trials where the probability of success is a lowercase p, we use the formula the probability that x equals k, and like I said, we'll dissect this thing, so we'll just write it down and stare at it for a little bit, is going to be equal to, and in round brackets here, n choose k. So if you haven't seen this notation, we will talk about it, right? So there's no fraction in here, it's just nk. So nk, so n choose k, times p to the power of k times 1 minus p to the power of n minus k. All right. let's deal with this portion first. So the probability that x equals k this you can just read as the probability of k successes, right? Just ignoring that x equals k. X is the random variable. It doesn't really do anything for us in this course, right? But it's supposed to be there, so we're just going to use it. So the probability of k successes, right? Which is what we said in the blurb, right? If we calculate if we want to know the probability of k successes in n trials, assuming that we know the probability of success, then we use this formula. So it makes sense that we start there. Let's talk about this guy. So here, you can read this as n choose k. This is how we're going to find the number of possible combinations, right? So this is what we did up here, where we went down our tree diagram, we had it mapped out, and we visualized it, right? But then I said, well, what if you have 10 trials? It gets really hard to visualize, right? You're not going to make a tree diagram, even though there's only two branches at each go, right? It gets out of hand. So the n choose k, right? This calculates the number of combinations, right? Of possible combinations. So n choose k, we don't know how to do it quite yet, right? But if you brought your calculator, I guarantee you that you're gonna have some sort of NCR function. It's usually NCR, and there it is. So on your calculator, you will have an NCR or some sort of something like that, right? It could be NCK, but I think usually it's NCR. Button. So how you use it typically is you feed it N and then hit the NCR button and then feed it R, right? Or in our case, we're calling it K just to match the binomial, but it's just N choose R. So I think, let's see here. So if you just try it on your calculator, because what we're saying is that we know that 3 choose 1 should give us 3. That's not very helpful, right? Because we're getting back to a number that we started with. How about 3 choose 0 instead to make sure that we get 1? Right? So if you do 3 on your calculator, and then I have to shift NCR, but then I get a little indicator of C. So 3 choose 0, enter, and I get 1. Right. So on your calculator, so to calculate 3 choose 0, you hit the 3 and then hit the NCR button. Oops, made my button round. and then hit the 0 button, and then I get 1. So just as an example, how many ways can we get 1 tail in 10 trials, right? So how many ways can we get 1 tail in 10 trials? We're going to calculate 10, choose 1. So 10, choose 1. I get 10. That's pretty boring. How about 2 tails? Ten, choose 2. 10, choose 2. 45. Yikes. So all of a sudden there's 45 different combinations that would almost certainly, one of those you would miss if you were trying to do it by hand, right? Even if you had mapped it out beautifully, one of those 45 would probably go missing. So that's when we need this binomial distribution, and we need to know the number of combinations, right? And so that's why we need this function. And on your formula sheet, right, in case your calculator does not have a choose function, it will. And if you can't find it, I'll help you find it. But I think all kind of very basic scientific calculators will have a choose function. And so on your formula sheet, we've got n choose k. There is a formula for it. Is n factorial over k factorial times n minus k factorial. If you're not familiar with the factorial, n factorial is n times n minus 1 times n minus 2 all the way up to till you get down to 2 times 1, right? So 4 factorial would be 4 times 3 times 2 times 1. So example 4 factorial is 4 times 3 times 2 times 1. We don't have to use this. We don't have to do this. I'm just pointing it out just so that you have it. And just as a fact, 0 factorial is just 1. I don't know why. There's a proof out there somewhere, I know it, but I have not investigated. Okay? So, but it does make it convenient, right, in case you've got 0. Okay? So we've kind of beat this to death here, right? The n choose k portion. Let's talk about the p to the power of k free. P to the power of k, well, p, it's the probability of success to the power of the number of successes. To the power of the number of successes. Right? If you think about our original tree diagram that we said, well, because the probability of 1 tail even if they're not the same heads and tails, right? Let's say the probability of heads was 0.6 and the probability of tails was 0.4, right? Mix it up a little bit. Well, it doesn't matter where I put that one tail, right? The probability of getting a tail is p, which is 0.4, right? And I've got one of those, which means the remaining number of outcomes, right, have to be failures, right? And so let's go back up here. That's where this next portion comes from. 1 minus p to the power of n minus k. 1 minus p to the n minus k. This is the probability of failure right, 1 minus p to the power of the number of the failures. To the power of the number of failures. Which in n trials, if k of them are successes, then n minus k must be failures. I will say this here, and I know I'm gonna get questions about it later, but often 1 minus p is written as q. So if you want to shorthand it a little bit, right? And sometimes I slip up, I try to use 1 minus p, but sometimes I'll slip up and use q, and it's just 1 minus p, right? P and q. But 1 minus p is the probability of failure, which is the probability of failure. So this is the formula that we're going to be using, right? It's on your formula sheet. But there's a couple of other things I want to talk about before we go ahead and do an example. So we can actually calculate the mean number of successes and the standard deviation for the number of successes, which doesn't really make sense until we talk about the normal approximation to the binomial. Okay, so for now, but the mean and the standard deviation can be calculated even if the normal approximation doesn't apply, which we'll get to. And so a binomial distribution has a mean number of successes and standard deviation. Where mu, right, is the mean, we can calculate as n times p. Which, if you think about it, if I tell you that you're flipping a coin 10 times and the probability of tails is, well, let's say 0.4 to make things a little bit interesting, right? So then the mean number of tails that you're expecting to see in your mind, you would say, well, then I'm expecting 10 times 0.4, right? 4. So I'm expecting to see 4 tails if that's the probability, right? And so in our heads, we already have this on lockdown, right? It's just now we've written it down on paper and now it's real. This is the mean number of successes, right? Because P is the probability of success. All this talk of success and failure means that the first thing that you're going to do when you tackle one of these problems is to identify, well, what is a success in this case? What is it that I'm interested in talking about, right? What's the probability that I know? Okay. And sigma squared is n times p times 1 minus p. So this is the variance of the number of successes, but leave that out, which means that the standard deviation is a square root of that n times p times 1 minus p. Notice that all we're using here is n and p, right? So that's kind of nice. All we need to know is the number of trials and the probability of success, which has to be given to you in the problem, right? And so you have everything that you need to find the mean and the standard deviation in this case. Right? So here, this is the standard deviation. And these are also on your formula sheet. Notice that all these calculations only require n and p, which will be given in the question. Which will be given in the question. Yeah. K is usually in the part, so it'll say something like, what's the probability of getting 15 tails? Right? So that'll be kind of, so in the core information, usually it's only n and p. And then in the follow-up parts, it'll say, okay, now what's the probability of 15 tails if you flipped it 20 times, for example? What's the probability of at least 15 tails, right? Something like that. And so what you can do, right, is just remembering that the binomial distribution calculates the individual probabilities, right? So for situations where you want to know if the probability of 8 or more successes, right, in 10 trials, then you would have to find the probability of 8 plus the probability of 9 plus the probability of 10. Right? And so the probability that x equals k equal to n choose k p to the power of k times 1 minus p to the n minus k. This formula only finds single probabilities. Right? Finds single probabilities. So let's say we have in 10 flips of a coin, what's the probability of at least 8 tails? What is the probability of at least 8 tails? When we're flipping a coin, it's safe to assume that we've got a 50-50 probability, right? So 0.5, 0.5. I was only using the 0.6, 0.4 just to illustrate, and so it doesn't get so monotonous with the 0.5, 0.5. But here, if I just say you're flipping a coin, let's just assume that it's even. Okay. So what would you have to do, right? You would have to find the probability that x equals 8. Actually, I'm going to say the probability that x is greater than or equal to 8. is the probability that x equals 8 plus the probability that x equals 9 plus the probability that x equals 10, right, in 10 trials. So what you're doing here is you've got 3 individual calculations, You're still allowed to use the 1 minus trick. Right? If I wanted to know, okay, in 10 flips of a coin, what's the probability of at least 2 tails? 2, 3, 4, 5, 6, 7, 8, 9, 10. You'd have to calculate all those probabilities. Or you could say, well, that's going to be 1 minus the probability of no tails or 1 tail. Right? And so, oops. What is the probability of at least 2 tails? Right. In 10 trials. Referring back to that question. And I'll even scoot this so it's on the same page. Well, the probability that x is greater than or equal to 2, right, at least 2, and I'm going to use shorthand note. I'm not going to use the x equals, and you're allowed to do that, right? You could say the probability that 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7 plus the probability of 8 plus the probability of 9 plus the probability of 10. Oops. Yikes. Or the probability that x is greater than or equal to 2 is going to be 1 minus, and then all in brackets, right? Because you have to subtract the probability of 0 tails and the probability of 1 tail from here. Right? So 1 minus the probability of 0 plus the probability of 1. Oh. I know which one I'm choosing. Right? Here, there might be some satisfaction in calculating all those probabilities, but probably not, right? And so I'd rather calculate 2 of these probabilities instead of, I don't know, 9, right? So you want to kind of map out which way is going to be easier, right? What if today's lecture is just a bunch of what ifs? What if you had this? What if you had this? Just becomes out of hand. So what if, though, I wanted to say, okay, I'm going to flip a coin 200 times. What's the probability that I get at least 50 tails? Are you kidding me? 200 flips, at least 50. There's no easy way to do this, right? And so what happens is, as long as we have a large enough sample size, gets kind of weird, but what we can do, because we can calculate the mean and the standard deviation, if we have a large enough sample size, we can actually use z-scores to approximate the probability. What? That is so weird. Tell me more. Okay, got it. So the normal approximation is going to be one to hang on to. The normal approximation to the binomial assuming we have a large enough number of trials. Okay, so that's a big assumption, and we will need to check it. Assuming we have a large enough number of trials, we can calculate probabilities, binomial probabilities, using a Z distribution. So assuming we have a large enough number of trials, we can calculate, or I'll say we can approximate, because they're not, you know, true, but they're good enough. We can approximate binomial probabilities using the normal distribution, and Z scores. Okay. So what's large enough? So we must check, and I'll write it in pink because it's important. We must check that n times p, which is your mean, right? If you're thinking about, we've seen n times p before, right? N times p has to be greater than or equal to 10. Right? That's just the rule, right? It takes into account p, if p is really small. So if the probability of success is really, really small, then you have to have a huge sample size in order to use the normal approximation, right? Just to be able to capture these successes. But also n times 1 minus p has to be greater than or equal to 10. This is essentially the number of successes is n times p, so we can say that this is basically at least 10 successes and at least 10 failures, right? Because 1 minus p is the probability of failure times your sample size, and so we have to expect, I'll put that up here, we must expect at least 10 successes and at least 10 failures. Which means that the absolute smallest sample size that you could use the normal approximation for is 20, right? But if you don't have at least 10 successes and 10 failures that you're expecting to see, right, then you need to have a larger sample size, right? You have to keep going and going in order to use the normal approximation. So here, you have to check these conditions to make sure, and they will be greater than 10 usually, right? Pretty safe. But once you've done that, right, if NP is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we can use mu is n times p, and sigma is the square root of np 1 minus p. And z equals x minus mu over sigma to approximate probabilities. To approximate probabilities. Pretty cool. How about an example? I know wearing you down. But that's all the theory around binomial distribution. So now we've got it all under control here. We just need to see what it looks like when we apply it. So if we have a look at question 4 on your handout, and like I said, I still have a couple of those handouts here, so you can grab them. So it says that the S&P 500 index has a probability 0.56 of increasing in any week. So assume the change in the index in any given week is not influenced by whether it rose or fell in the previous week, which is kind of a simplification of what actually happens, right? With stocks, we know that they kind of rise and fall together. But we're saying, hey, let's ignore that so that we can use a binomial distribution. Let X be the number of weeks among the next 5 weeks in which the index rises, right? And so from here, we've got the number of trials. We're looking at 5 weeks. The probability of success is 0.56, which assumes that a success is that the index is rising, right? And so I guess it's in part B and C. So I guess I'll just calm down and answer these parts one by one, right? But that's how you want to approach these problems, because it won't always feed it to you like that, right? You'll want to read these problems and figure out, well, can I use a binomial distribution, right? Do I have success failures? Do I have outcomes that are independent of each other, right? Here we're saying, yeah, we do, right? What's the success? The index rising. What's the probability of success? 0.56, right? And so how many possible outcomes are there each week? In each week, it can either go up or go down, right? So we've essentially got this success failure, right? So there are 2 possible outcomes each week, right? It can either increase or decrease. I'll add in, right? Since we assume each week, or assume the weeks are independent, a binomial is appropriate. Right. Because that's what you would argue in your mind, right? Not just the first part, but also that second part that I added. So part B, identify what a success is in this case, right? So in this case, we said a success is an increase. Thanks. Part C, what are N and P in this case, right? And so here we said N is the number of trials. Well, that's how many times we are able to get a success, right? And we're looking at 5 weeks. So N is 5 because we're looking at 5 weeks. Right? Each week has an opportunity to have a success, right? Each week can have an increase. And so we have 5 trials, or N equals 5. And we said P is 0.56 because that's the probability of it increasing in any week. So 0.56 0.56, which is the probability of success. What are the possible values of x? So x, or k if you want to, right? How many successes can we have in these 5 weeks? So d x, well, in 5 weeks, I'll use set notation, you don't have to. X can take on values, well, there could be 0 weeks with an increase, making all of the weeks decreasing. Like what's happening right now. 0 increases, 1 increase, 2 increases, 3 increases, 4 increases, or 5 increases, cha-ching, right? And then that's it. So these are the possible outcomes: 0, 1, 2, 3, 4, and 5. And those squiggly brackets, right, that's just to denote that this is a set of values, all the possible outcomes of x. You don't have to have them there. You should, but you don't have to if you don't like them. Not in this course, at least. Part E, what's the probability of the index increasing in more than 3, not including 3 of the weeks? Okay. So now we have to figure out, okay, well, more than 3, not including 3, that would be 4 or 5, right? Increases in 5 weeks. And so we want to find the probability of 4 plus 5. So E, if we write it in probability notation, the probability that x is greater than 3, right? Because it said not equal to 3, but just more than 3. Well, that's going to be the probability that x equals 4. And like I said, you can skip the x equals 4 and just write p of 4 if you want to. Sometimes I'll do it and sometimes I won't. Depends on how lazy I am. Probability of x equals 5. Add it in there. Sometimes these calculations are way too much to have on one line. So what I often do is I break it off and I find p of x equals 4 and then separately from p of x equals 5, and then I bake them back in, right? And so we can solve these individually, especially because we haven't actually done a full-on calculation quite yet, right? And so we can solve these individually and say the probability that x equals 4, and that's why I wanted to have x equals 4 in there to show to the general formula that you have, right? You know what? I'm going to write the general formula. The probability that x equals k is n choose k times p to the power of k times 1 minus p to the n minus k. So now it's easier to map the 4 to the k, for example. But once you have that under control, no, you don't have to write the x equals in there. So the probability that x equals 4, we said that we have 5 trials, right? So we've got 5 choose 4. Remembering that's not a fraction, it's its own thing, right? So I don't want to see any lines in between there. 5 over 4, no, it's just 5 choose 4. P is 0.56 to the power of, and now we're talking about 4 successes, times 1 minus 0.56 to the power of 5 minus 4. So first thing we're gonna do, right, is calculate 5, choose 4 on our calculator. 5, choose 4. Womp womp, it's just 5. All right, so 5, choose 4 is just gonna be 5. And I'm gonna keep the 0.56 to the power of 4 as it is, but I'm gonna simplify the 1 minus 0.56 to 0.44 to the power of 5 minus 4, which is 1. Then I can multiply this through here. So I've got 0.56 to the power of 4 times 5 times 0.44 is 0.216358912. You want to keep as many decimal places as you can. Must keep as many decimal places as you can. And just because I'm stubborn, we're going to do the probability that x equals 5 as well. 5, choose 5, 0.56 to the power of 5. 1 minus 0.56 to the 5 minus 5. If you do 5, choose 5 on your calculator, and even if you visualize your tree diagram, right? If you want every single one to be the exact same, there's only one way for that to happen, right? Going down one of the outsides of your tree diagram. So 5, choose 5 is just 1. And then 0.56 to the power of 5. And then 0.44 to the power of 0 is just 1. So we get 0.56 to the power of 5. 0.05507311776. Now we can combine these and say that the probability that x is greater than or not equal to 3, I almost said it, greater than 3 is the probability that x equals 4 plus the probability that x equals 5, which was 0.216358912 plus 0.05507311776 plus 0.216358912. I get a total probability of 0.2714320896. I'll leave the last one for next day, but you can absolutely go through and have a look at question 4, the rest of question 4 and question 5, and then question 6 is the Poisson. See you guys on Wednesday. See ya.